flavor puzzle. So, as you know, we all know that the standard model works. We recently celebrated the 10th anniversary discovery of the Higgs boson, if you want the completion of the standard model spectrum. However, we also have many good reasons to think that this is only an effective theory. So the standard model is just the low energy limit of something more complete. So, and the data tell us that there is a mass gap between this standard model sector and what's above. Okay, but still we think this is an effective theory. So if you want in this perspective where the standard model is an effective theory, we have identified the long range properties of this effective theory. Indeed, everybody called now this the SMEF, that is the low energy limit of a bigger theory, where the low energy degrees of freedom are the standard model field. So as I said, there are several reasons why we think that there has to be this ultraviolet completion of the standard model here, at least some of the most pressing in different categories. So we have the electroweak hierarchy problem, the flavor puzzle, the neutrino masses, and then finally we have cosmological observation like dark matter, dark energy, and finally the fact that we cannot embed quantum gravity in a consistent way in any quantum field theory right now. However, these problems are on different grounds, and particularly the first category here, the first two categories here are interesting really from the point of view of an effective theory, because they're problems that we can handle in quantum field theory, and they signal some peculiarity of our Lagrangian, okay? Some tuning, something that I think call for a deeper explanation still within within the domain of effective theories or quantum field theory. While, for instance, for the cosmological observation, it's much more difficult to assign a precise scale. So we don't even know if this is a problem of quantum field theory or if something related to observation. So it's much more difficult to address it in the context of quantum field theory. And so this is why I think we should really try to attack this problem first, or at least if we really want to describe things using quantum field theory, these are the things we cannot ignore. And in particular, in this talk, I will focus on the flavor puzzle, which is a very interesting message. I think I will try to convey. It's a very interesting message coming from the ultraviolet. So this peculiar flavor structure that we observe in the standard model, you can think of it really as a message coming from the UV that we need to decode. Okay, so that is really my if you want, general take on the standard model. On the flavor puzzle, sorry. So what is the puzzle? I think this is well known since now more than 50 years, and I think probably the best way to introduce the puzzle is to have these two quotes of two famous Nobel laureate, Nobel Prize winner. One is Isidori Rabi, who already in the 50s said, who ordered the muon when the first copy of a particle, with exactly the same quantum number as the electron was found, that is the muon. Clearly, this was the first indication of a puzzle, why we have these additional particle, okay? And of course, the problem remained and became much more evident later on. And I think I also like very much this quote by Weinberg, who said, again, one summer of quite many years ago, that he was trying to address this problem. Okay? The problem is that we have this spectrum of masses that seem to hint to an underlying principle, organizing principle, but it's very hard to pin it down. Indeed, as he said, it's been this puzzle was there. He was hoping to solve it with the standard tools of symmetry and symmetry breaking, but then, of course, he failed because otherwise we would know it. And this is a frustration, as he said, because it's for a long time has been a frustration, the fact that we don't have really a clear clue on addressing this issue. But so let's go for order now. Beside this quote, let's look at the problem in more quantitative terms. So first of all, we have to realize that there are two independent problems. Okay, one is what I would call the standard model flavor puzzle, which is the one that I illustrated with these two quotes. That is the pattern of the Yukawa couplings, which correspond to the pattern of quark and lepton masses, is quite peculiar. It's very peculiar, and it seems to hint to a deeper explanation, to hint for a possible deeper explanation in terms of symmetry and symmetry breaking. The second puzzle is the fact that if the standard model is only an effective theory that is valid below a certain ultraviolet cutoff, why we don't see any deviation from the standard model prediction in several processes which are extremely suppressed when we look at flavor changing process, which therefore could be naturally very sensitive to physics beyond the standard model. So this is what people usually call as the new physics flavor problem. These are two independent problems. Again, let's now be more quantitative on the first problem. As I said, what we mean by the pattern is not accidental. Well, again, let's look first at the CKM matrix, the matrix describing the mixing of quarks. As you know, this matrix is very close to diagonal, to be a unity. These entries, which I denote with black, are essentially 1, and the other entries are very small, and especially there is a block, the 2x2 block, which is very separated from the third generation. Okay, so the mixing between third generation and first two is very small. Indeed, the unitarity violation of the first of this block here are below 10 to minus 3, which is quite peculiar. And indeed, despite the case of precision measurement in flavor physics, basically we are not able to detect the presence of the third family by looking only at the 2x2 block, okay, just by unitarity. It's impossible because it's too small. And actually, this is an interesting message. It's telling us that actually, if there are extra families or extra field that mix with the standard model one, we should not be discouraged by the fact that we have not seen any violation, because I mean, it's simply if the mixing is small, it's hard to see it. But then the flavor structure of standard model are not only this mixing term. The real element that enter in the Lagrangian are the Yukawa coupling. So this element Y that couple, for instance, in this case, the quark doublet to the quark singlet in the up sector is a 3x3 matrix. And this 3x3 matrix is even more peculiar because here there is a single entry which is close to 1, and all the others are very small. So actually, this is a combination of the mixing and the eigenvalues. So the mixing are determined by the CKM matrix, and then the eigenvalues are related to the quark masses. When we put these two information together, we find this matrix which has a very peculiar structure with a single entry of order 1, which is the top mass, and then it ranges 5 orders of magnitude, okay, from the smallest entries here, which is the mass of the up quark. So why this is so? Clearly, this doesn't look accidental, okay? This 5 orders of magnitude span on a parameter in the Lagrangian. We would like to have an explanation for that. And to be more quantitative also, because this will be important in the future, what we seem to observe in the Yukawa coupling is an approximate U2 symmetry. This U2 symmetry is a symmetry acting on the Lat families. So here you see, this is the Yukawa interaction. So interaction between the quark doublet and the quark singlet. These are triplet in flavor, I mean, because there are 3 flavors for this field and 3 flavors for this field. Now, if I say that there is a U2 symmetry acting on the light generation, on this field here and on this other field here, these are 2 different symmetries. In the limit of when these 2 symmetries are exact, these will be global symmetries. I would forbid all these entries except the third generation one. And numerically, these are very small entries in the standard model Lagrange. So it looks like there is an approximate U2 to the n, when n is the number of independent fermions that we observe acting on the light families. This is a way to express this puzzle, observational puzzle, if you want, in the Yukawa coupling. But as I said, this is only one part of the problem. The second problem is that if the standard model is only an effective theory, value below a cutoff, why we don't see anything else besides this peculiar Yukawa coupling? And so to quantify this problem, so the so-called new physics flavor puzzle, we have to be more precise and introduce better the concept of the standard model as an effective theory. So let me open here a bit of a parenthesis. So what we mean technically by the standard model as an effective theory. So this is the Lagrangian of the SMEF, the standard model interpreted as an effective theory. Contains 3 pieces. It's the gauge sector, which is the gauge sector of the standard model Lagrangian. Then we have the Higgs sector. And these are all the interaction of dimension up to 4. So the part, the normalizable part, what one classically would define as the standard model, which, if you want, is is the long-range structure of our effective theory. Okay, what describe what we observe at large distances, the interaction and the field, and the Higgs sector determine also the ground state. Okay. All the rest, if any, in an effective theory language, can be described by point-like interaction, like Fermi-type coupling. So if there is some heavy new physics, this heavy new physics, by definition, is heavy, so we don't have enough energy to excite it, and it looks like at low energies as a point-like interaction. So this is the remnant of the heavy degrees of freedom. It's a completely general description. If we classify here all the operators written in terms of standard model field, we completely classify how to describe heavy new physics. Now, the key question, if you want, probably the most important question in particle physics nowadays is which is the cutoff scale of this effective theory. And the cutoff scale appear here as the dimensional scale that suppresses this contact term. You see, if there is some new interaction here controlled by some heavy scale, this heavy scale appear at the denominator of this operator with powers which increase depending on the dimension of this operator, on the canonical dimension of this operator. Now, a somewhat vague but useful information on what is this cutoff scale comes from the famous electroweak hierarchy problem, because here in the Higgs sector, there is a quantity, which is the Higgs mass, which is quadratically sensitive to the cutoff of the theory. So what we measure, which is the physical mass, is the result of a parameter in the Lagrangian, which is defined, if you want, at the cutoff scale, and then correction, which are quadratically dependent on the cutoff. And by cutoff, I mean all the quadratically dependent on the masses of the heavy new physics. If this heavy new physics coupled to the Higgs with coupling of order 1, then we will expect really correction proportional to lambda square. So clearly, since the Higgs mass is small, okay, we measure it is 125 GeV, this cutoff cannot be much higher than what we measure. Otherwise, we have this tuning problem. So this is a qualitative argument. It's not very quantitative because, of course, we can cancel these two with some accuracy. But is an indication that it's hard to think that the new physics is too far away from the electroweak scale. So some new physics couple at least to the Higgs and to the top, which are the two particles coupled with strength 1 to the Higgs sector, they have to appear in the TB scale. Now, speaking only of a single cutoff for the SMEFT, which sometimes you see this discussion, I think is a very dangerous and a bit oversimplifying. Is a way to oversimplify the problem, because indeed a closer look to this question reveals a series of layers. First of all, indeed, here this lambda is an effective scale, and in general, when you have exchange of new degrees of freedom, you will have not only a scale, but you have masses and coupling. So actually, this lambda will be a combination of mass divided by coupling, okay? And of course, this mass coupling ratio can change a lot depending if the new physics is weakly or strongly coupled. Still, this is actually often discussed, but this is only one part of the problem. Then there is an extra layer, which is in a sense even more important, which is the flavor structure, because we have several degrees of freedom here in our Lagrangian, the different flavor, and therefore there are a lot of possible ways to couple the new physics, which will determine this operator, to our low energy field. And you see, this is somehow illustrated by these numbers. So if and the way the new physics talk to the standard model can change a lot depending on the flavor structure of this new physics. This new physics see the different generation in a different way, or it is blind. And from the Yukawa sector, we know that flavor physics is highly non-trivial, because we see that these Yukawa coupling are not at all identical. And you see the number of parameter encoding flavor physics here in this math is huge. Indeed, if we don't impose any flavor symmetry, we have 2,500 free coupling in this math, which is a huge number of free parameters controlling all possible for quark or for fermion operator. But if we impose a flavor symmetry, so we assume that new physics couple completely universally, then we reduce this 2,500 to 50. So clearly the dimension of flavor in describing the SMEF is crucial, okay? And this new physics flavor problem is exactly about that, I mean, which is the flavor structure of new physics. So to understand which is the flavor structure of this effective operator, we first have to summarize what we see here in the standard model. So in the standard model, we have two things. The gauge sector is completely flavor blind. So the gauge interaction do not resolve flavor, okay? Actually, technically, this means that there is a symmetry, an accidental symmetry in the gauge sector, which is a U3, because we have 3 different flavors, to the 5th power, because we have 5 different type of fermion field, 5 field with different gauge quantum number. Then this large flavor symmetry that is defined by the gauge sector is broken in the standard model by the Yukawa interaction. But as we have already said, the Yukawa breaking is very peculiar. So only certain coupling are big, all the others are small. And also is a specific left-right structure, like left-right mixing. We don't have left-left or right-right. This is forbidden by the gauge symmetry. And therefore, this I call it a peculiar breaking. So in the standard model, we have this combination of a large flavor symmetry and the peculiar breaking, which, as the result, give rise to a series of approximate that we usually call accidental symmetries. For instance, individual lepton flavor is an exact symmetry of this part of the Lagrangian. It's accidental because we don't impose it. It simply comes out automatically by the property of gauge interaction. We cannot break individual lepton flavor at the level of dimension 4 operator. But there are also other symmetry, for instance, isospin, which is an approximate but still very good symmetry, which results from the fact that up and down masses are very small. So the Yukawa coupling here corresponds to the mass of the up and the down are very small. And this what gives rise to isospin symmetry. So it's really this combination of the large flavor symmetry and the peculiar breaking that define the flavor structure of the standard model. So what about this term? Clearly, this term is the puzzle. Okay, we for the moment we don't see any deviation from this sector here. So the question we need to quantify is how these accidental flavor symmetry that are defined by this sector here are broken in the SMEF. Okay, and to again be more quantitative here, but let me first open a parenthesis and discuss a bit more in general some of this concept of accidental symmetry. So what we mean by accidental symmetry? Accidental symmetries are symmetries which are not fundamental properties of the theory, but emerge accidentally at low energies, simply because we don't have enough variable to describe the violation of the symmetry. So here, the operator that we have here is that do not allow to describe a violation of a symmetry. They do not allow to describe a violation of lepton flavor. Okay, but so it's a bit like the multiple expansion. If you look something from far distance, everything looks spherical because you just look at the leading multiple, which is the monopole. And then when you go closer, you have you see more, so you start to resolve the dipole and so on, and then you break the symmetry. So you start from a spherical symmetry, then you go to a cylindrical symmetry, and then less and less symmetry. So if the symmetry is violated by some new degrees of freedom that happens here at higher energies, then this violation should be present in the contact interaction. So if the symmetry is only accidental and not exact, you expect to see it via the contact interaction, the higher multiples. And that's exactly what happened in history many times. Actually, in the building of the standard model, we use this concept. And I think here is interesting to illustrate this with an historical fact. If you take the standard model with only 2 families, so I call now the standard model 2 effective theory, there CP violation is an accidental symmetry, because with only 2 families, you cannot describe CP violation in the standard model. You can completely remove the phase. And when the standard model indeed originally was formulated, that was indeed a theory with only two families, and basically was somewhat completed with a Gene paper. Indeed, one could describe everything except the CP violation observed in chaos mixing. Okay? epsilon k. And that was indeed was clearly a remnant that there is something else, some heavy new physics. And indeed, the famous super weak interaction proposed by Wolfson, actually even before the standard model was discovered, if I reinterpret in modern language, was exactly a point-like interaction containing a four fermion operator that describing mixing with a phase. And if I assume this phase to be order 1, the scale of this operator that I need to describe K-bar mixing is huge, it's 10 to the 4. Okay. Now we know that this scale, actually this is indeed a good description of what happens at low energies, but this effective scale is a complete mirage, because we know that the correct theory is not the standard model 2, but it's the standard model 3, and this scale actually is calculable in terms of the top mass. So the degrees of freedom in the standard model allow us to describe superpopulation is the third family. And so this scale is calculable, and it was computed by Ellis and company, and that's how you get the correct description of epsilon k. So you see that there is nothing at 10 to the 4. Actually, the new degrees of freedom happen at much lower scale. So the effective theory description is useful, it's telling you that there is something, but when you try to extract the scale, you have to be very careful. So the important message of this EFT approach is that seemingly high scale in the EFT can be mirage, okay? Actually, they usually are somehow an upper bound on where you can expect the new physics. So now let's go back to our standard model. Actually, better standard model EFT with 3 families. So in principle, we could expect many violations of the accidental symmetries from the heavy dynamics. But for the moment, we don't observe any clear deviation. And this is the new physics flavor puzzle. And the way to express this puzzle is somehow to put bounds on this effective operator from the non-observation of violation from the standard model prediction. So for instance, the strongest bound comes from, again, actually from K-bar mixing or all the other mixing of meson anti-meson. These bounds are usually expressed as bound on a scale, which is the scale of the corresponding operator. Just putting a coupling 1, okay? So if I put the coupling 1 and I measure, for instance, K-bar mixing, I compute the contribution from the standard model, and then I see what else can be there in comparison with the experiment. This is precisely measured, and I find these bounds on the scale, which are extremely strong bounds. But again, exactly, I did this discussion about K-bar mixing before to stress the fact that these bounds should not be overemphasized. So this scale, this high scale, which are often advertised, can be a mirage, exactly as it was a mirage, the 10 to the 4 in the standard model 2 that actually turned out to be the top mass. So the only, however, there is a clear message from this scale, is that there is no large breaking of the approximate U2 to N flavor symmetry at nearby energy scale. So if this new physics, if it is nearby, should respect the approximate symmetries which are present in the standard model Lagrange. And what is peculiar is that this U2 actually is not a natural accidental symmetry of the standard model. Okay, actually, in the gauge sector, we have U3. So why we have U2? See where this comes from. So can be an indication of how we have to complete the standard model. That is the important message we have to address. So summarizing this first part, I mean, what we observe, so the puzzle that we observe are summarized by these 3 points. So the standard model EFT has a gauge sector which is fully symmetric, no distinction about the 3 families, which is a big flavor symmetry. In the standard model, this symmetry is broken by the Yukawa coupling, and this Yukawa coupling somehow induces a breaking of the type U3 to U2, okay? Which is rather peculiar, we don't know why, it's an observation, okay? So essentially only the 3rd families acquire mass. And in first approximation, the light families remain massless. And then all these extra degrees of freedom, if they are there, they seem to respect this. So they seem to respect these U2 symmetries. They don't destabilize it. Otherwise, we would have seen violation in K-bar mixing, B-bar mixing, and so on. So the 2 questions is, can we find an explanation for this type of breaking? And can be this breaking associated to some, true accidental symmetry? So the fact that we really have, we find a way where we have U2 and nothing else. I mean, so these are the questions we would like to address. And to do that, we really need extra hypotheses. So we need more dynamical hypotheses, so we cannot just stick at the EFT level. And so this brings me to my second part, which is this idea of flavor non-universal interaction. Okay, so by the way, please interrupt anytime. I sometimes tend to say many things. I forgot to tell this, I should have said before. Please interrupt me anytime.
Yes, and Gino, I have a question.
Sure.
The U2N, what is the N that you have there?
Yeah, thanks a lot for the question. N stands for the number of independent fields that we have, which is at most 5, because we have 5 fields with different gauge quantum number. No? So we have the quark doublet, the lepton doublet, and then we have U right, D right, and E right. However, one can even think of cases where there are less, maybe we have the same symmetry acting on different, on more than one of, so together, for instance, E right and D right, so we can have a smaller group.
Okay, thanks.
Okay, but this is really related to the number of independent fermion field. Thanks. Okay, so, you know, before discussing this idea of multi-scale, let me first discuss the old idea of basically a single scale or a two-scale problem. So for a long time, a lot of model building was based on the idea of assuming a flavor universal new physics. The idea was somehow the following, illustrated by this cartoon. So the idea that, okay, we need some new physics close by from the electroweak scale to stabilize the Higgs, because we have this hierarchy problem in the Higgs sector. Now, the most efficient way to do to protect flavor is to assume that this flavor new physics is flavor blind, and the breaking of flavor comes from the Yukawa, which, however, are generated at some very, very heavy scale. This is technically possible because the Yukawa are numbers, are dimensional numbers, so they can be generated from heavy scale. So this BSM was supposed to be flavor blind. So this is a typical hypothesis in the MSSM, the minimal supersymmetric standard model. You assume the Yukawa are generated at the gut scale very far. So what you feel here is just the breaking of the flavor symmetry via the Yukawa, and therefore flavor physics is somehow protected. This is also goes under the name of minimal flavor violation paradigm. So the Yukawa coupling are the only source of flavor symmetry breaking accessible at low energy. So this way, we achieve somehow a separation of the stabilization of the Higgs sector and the flavor problem, which is somehow the flavor problem is not solved, but is postponed to a high scale, which is technically possible. And the underlying idea here is that the 3 families are identical copies up to high energy. So basically, this structure with 3 generations, they remain the same. And also the gauge structure is the same up to high energies. We basically only stabilize the Higgs. I think this was a very good idea before the start of LHC, because could lower the new physics scale here. However, now this has become less interesting because we don't see new physics coupled universally at the LHC. At the LHC, we collide protons, which contains up and down quarks, first approximation. So if there was new physics coupled universally, we would have coupled also to up and down quarks, which are inside the proton, and we don't see them at the TV scale. Okay, so the bounds in this with universal new physics are becoming stronger. So we cannot really, we have a more serious tuning with the Higgs because we have strong bounds on universal new physics. So there is a worsening of the Higgs hierarchy problem under this idea of minimal flavor violation, because we assume new physics coupled universally. Now, if I give this cartoon, I very briefly illustrate the bounds on the new physics coming from LHC, then we will come back more precisely. But the message I want to give is that if we look at universal new physics, so new state coupled also to the up quarks inside the proton, then the bounds are very strong, around 10 TeV. If you look at these other searches, which are searches only for 3rd family new physics, so some fields which are coupled only to B top tau, then the bounds are much weaker, around 1 TeV. So you see there is a difference in new physics in the bounds that we have on new physics coupled universally, which are quite strong, 10 TeV, compared to bounds on new physics related to the third family, which is 1 TeV. So this is why I think now a much more interesting paradigm is to assume that new physics is not flavor blind. And actually, new physics see differently the different generations. So the basic idea that address much better these, both the flavor puzzle and possibly also the Higgs, is the idea of a multi-scale theory. There are different scale, and actually the new physics, the different scale characterize where new physics talk to different families. So new physics talk to the third families at low energies, and therefore, and this is why also the third family Yukawa coupling is big, and the Yukawa coupling of the first two families are small because they are generated at higher scale, so they are more suppressed, and actually this also protect the light families from being contaminated by new physics. So this is the picture. Let's now try to make it more quantitative. But before doing that, before being quantitative, let me give you an illustration of somehow the shift of paradigm, which I think it's important. You actually see, I put here some quotes. I think these are all the ideas, but on which there's been quite a lot of recent interest with concrete construction. But before entering the construction, let me make these simple, very naive illustration, which I think it's interesting. So consider the electron and actually the positron and the proton. And suppose you can probe them only with a low energy, very low energy photon, so long range photon. What you would say, if the photon is long range, does not see the proton radius, you would say, well, we have two particles which are identical, but for their mass, right? Then, of course, when you go to high energy, you understand that the proton is completely different from the electron. They are not identical particles. They are very different. But the low energy photons see them equal, exactly the same structure, because the only thing that matters is the charge. Okay? But you see, we can think that the same thing happened also for the three families, where now the long range, what I consider the long range gauge interaction, is the full sector of standard model gauge interaction. So you see, this argument of having three identical copies, when we say identical copies, is identical with respect to what? Well, they have the same charges. They have the same charges under the long range forces. However, these do not forbid to have very different charges for the three families under new forces, which are more short distance. Okay, so the fact that we seem to see identical copies, but for their mass, could be just a low energy accident. Okay, indeed, the fact of having different mass signal that there is some new physics there that will, if new physics determine the mass of this particle, new physics can be very different in the three. And of course, the only thing that survives at low energies is the mass. This is a general quantum theory argument, because the mass is the only relevant operator. Again, let me give you another example, which I think also is quite illustrative. Again, let's go back to the photon. And let's consider how the photon sees the electron with the two chirality. At low energies, I mean, electron left and the electron right, we think actually are the same particle, the same field with different chirality, right? Of course, this is QED. However, in the standard model, electron left and the electron right are two completely different fields. Okay, a really different object, okay, from the field theory point of view. And even the photon, our long-range force, it's not even, if you want, it's not associated to a single field at high energy. It's a combination of hypercharge and SU2 left. And these two fields is very differently the two different of course, this is something that we all know, but you see, something similar could happen also for flavor, okay? And you don't need to tune the charges of these two particles to have something identical at low energy. This comes automatically by the symmetry breaking structure. Actually, when you end up to having two groups and you break down to the diagonal subgroup, you automatically select the same charges here for the photon. So again, this is another illustration here. There is, if you want, an accidental parity, which come out from a theory which is not parity symmetric in the ultraviolet, okay? And parity emerge as a low energy property. In the same fashion, flavor universality of the gauge interaction could be a low energy artifact. And so this is the idea here is that really the interaction that when we go higher in energy, the interaction will be really different for the different families. So different families have different quantum numbers under an extended gauge group. And so the idea is that what distinguishes the first two families is something that happens at high scale. So actually, this is where the origin of the Kibbe angle appear. But all this happens at high scale, is somehow frozen at high scale. This is why we don't see any deviation from this U2 breaking structure, which is generated at high scale. And the imprint of this EFT construction is something that describes well what we observe in the Yukawa coupling. So something, Yukawa coupling, which is third generation large, then a small mixing between third generation and the light families, and finally, very small structure describing the Yukawa for the first two families. But again, this is what we can say only using general EFT argument. Let's now try to be sorry, I forgot this slide where indeed what we see then finally what you can probe in experiment is only this layer here, okay, where we have we expect a few TV new physics where this new physics should couple mainly to the third generation and somehow respect this U2 to the n flavor symmetry. So this is what we expect as a structure for the SMEFT if we assume that these ideas are correct. And so recently we have done, inspired by this general idea, we have done a global analysis of the SMEFT, so of all the operator, trying to see indeed how low can be this new physics scale if you assume a structure of this type, that is that there is a small breaking of U2 controlled by the Yukawa coupling, and then new physics couple essentially only to the third family. So let me illustrate the result of this global fit that we have done. So first of all, once you assume exact U2, you reduce a lot the number of independent operators. So in the limit of unbroken U2, you have only 120 independent operators. So in this table here, you see all the operators listed. Actually, they're not even all the 120 are the most important one, but we looked at them all from data. And then we have bounds on this operator, sorry, coming from flavor observable in the up sector or down sector, electroweak observable, and collider observable. And these are the different bounds on the scale if I simply assume coupling 1 divided by scale. You see that the bounds now, still some bounds are strong, like here we have, these are dipole operator, we have bounds which are up to 10 TeV, certain operator bounds which are again, well above 10 TeV. But for a moment, I've only classified operator using this U2 symmetry, okay? So basically, I don't distinguish in the light sector, but I distinguish between third family and light families. Now I have to implement the concept that new physics couple mainly to third generation. And you see, the operators which involve only third generation are here and are those where the bounds are weak, okay? As we have illustrated before when looking at the experimental bound. So the U2 symmetry alone simply allows to separate new physics affecting light families and the heavy fermions. And if you look at only the third families, only at operators involving third families, we found that the bounds are weak. So the question we ask is, how weak has to be the coupling to the light families to get at this level, which is somehow the bounds on the new physics coupled to third generation. So you see now, again, with the same analysis, we simply assume that there is a suppression factor for coupling to light quark and light leptons, such that the corresponding operator becomes consistent with this bound. Here, looking only at electroweak and collider observable. You see that we get already a much better picture, and also we put a suppression factor for dipole operator, which are generated at the one loop level. Finally, there is an issue about the U2 symmetry, because I have to tell you how, I mean, what is the third generation? So we don't know if the third generation is exactly the bottom or the top. So there is a mixing here, and so there is a free parameter that we can adjust, which is the alignment of one of the third generation. This is a bit of the technical point, but again, fixing also this parameter. And you see all these parameters are are not particularly tuned parameters, okay, we have been able to put all the operator with bounds below 1.5 TeV. So the message which I want to give you here is that new physics now really doing a conservative analysis of all these math operator. If you implement in a technical way the hypothesis that new physics is coupled mainly to third generation, the bounds that you get on this new physics are weak, are not super weak, but are at the level of 1 to 2 TeV. So not 10 TeV, not 100 TeV, 1 to 2 TeV. And there is an interesting, you see, once you implement this hypothesis, which again are very natural, you don't have to put too much weight to this number, but these are not the two numbers, okay? They're not 10 to minus 2 suppression. So what this just is a mild suppression of new physics coupled to light families, no suppression to new physics coupled to third families. Then we manage to keep the bounds at this level. And in this case, the bounds coming from flavor, electroweak, and collider observable are very comparable, which is also a very interesting message. Okay, now before finally going to some flavor observable, as I said, for the moment I discuss everything in terms of EFT approach. Let's now be a bit more model dependent, and let me tell you which can be the type of new physics that we are thinking about. Well, the interesting idea is this idea of flavor deconstruction. That is that we have gauge symmetries which act differently on the different generation. So the idea is that, in particular, if we just, here we have at low energies, we have a universality of gauge interaction, exactly like electromagnetism we discussed before. Is completely invariant under chiral symmetry. Then when we go higher, we resolve these difference between left and right field. The idea is that at all energies, gauge interaction are completely flavor blind, but when we go higher, gauge interaction sees the different families. So there is a gauge group for the third family and the gauge group for the first two families, which I denote here with G12. So if I assume something like this, and if I assume that the Higgs is charged under the gauge group 3, then clearly the Yukawa coupling for the third family is allowed by gauge symmetry, while the Yukawa coupling for the second family is not allowed, simply because here I would not conserve, this field is charged under a different gauge group. So if I stick to this level, at this stage, I have a Yukawa coupling which is possible only for the third family. So remember, so the Higgs is charged under G3. Then of course I have to break this setup and go down to the diagonal subgroup, which is the standard model. Actually, this can be for any subsector of the standard model. It can be for SU2 left, for SU2 right, or for hypercharge. When I break and I go to this diagonal, then of course there will be this field that breaks the symmetry, and therefore I can build effectively the suppressed term, but this will be described by effective operator, by effective higher dimensional operator. So I explain naturally this structure here. So this idea of gauge non-universal interaction high scale allow us to reproduce, if you want to trade the Yukawa hierarchy in terms of scale hierarchy. And this scale hierarchy is stable. And actually, essentially only 2 scales are required to describe everything. Now, going even more specific, so again, to summarize what these tools allow us to achieve is that, again, we have non-universalities among the two families, which is frozen at high scale. And so actually this allows us to pass the precision test. Then in this case, if we assume that at some intermediate scale, we have this gauge group acting on the first two families different from the gauge group acting on third families, I predict now U2 as an accidental flavor symmetry. And finally, at all energies, my imprint is in the structure of the Yukawa coupling, which is this message from the UV that we observe. So that is why this is the main idea. Now we have several options because we can discuss what is G, if it is SU2 left, SU2 right, or other groups. all the options have been classified. Actually, recently we have classified. There are not many consistent choices that because are basically related to the three group that we have in the standard model. A particularly interesting option, which I want to discuss here in slightly more detail, is the idea that actually the last symmetry breaking step is the one where we deconstruct flavor. Sorry, flavor deconstruct in flavor color. That is, rather than having SU3, which is SU3, the color group, what we observe as color group is a diagonal subgroup of a SU4 acting only on the third generation and SU3 acting on the first two generation. And then there is the electroweak group. So this is very interesting. In SU4, you know, in SU4, we achieve a natural way of explaining charge quantization because in SU4, quark and lepton are in the same multiplet. So the SU4 group proposed by Patrick Salam long time ago contains color, leptoquarks, and B-L. But we are using it only for the third generation. Right? Yeah. So the idea here, I mean, coming back to this picture, is that SU3 color emerge as diagonal subgroup of SU4 times SU3 in a very similar fashion to what happens at a lower scale where electromagnetism emerge as the diagonal group of SU2 left cross U1. Actually, this SU3 could be broken at higher scale from a bigger SU4 acting on the light families. This breaking should happen at higher scale. It's likely like U1 hypercharge can be embedded in SU2 right. So we are always looking at truly diagonal subgroup where indeed one doesn't need any tuning to achieve a universality. So here again, we, as you all know, we achieve universality in chirality in electromagnetism automatically. The same here, we would achieve universality in color automatically, starting from something which is not universal in flavor. Okay, so will be a different color for the light families and the third generation. This breaking should happen at the FUTV scale, but this breaking happens at the electroweak scale. Why we choose SU4? I mean, one reason, if you want, one theoretical reason is the charge quantization. Another more phenomenological reason is that actually when we do this breaking, one predict as a massive field coming from the breaking a vector leptoquark, because we have this vector leptoquark, and this leptoquark actually turned out to be a very interesting mediator for some anomalies which are still there in present data related to third generation flavor effect. Okay, it might explain some hint, some tension in B-physics data. So this brings me to the very last 5 minutes illustration of some phenomenological consequence of all these ideas. Starting from flavor data. So if this idea of a flavor non-universal interaction with a first layer of universality coming from below already at TV scale has several interesting implications for several low energy measurements. So the first one is that we should start to see some deviation in flavor observable involving third generation field. The most interesting here is this B2C tau decay, because here we have a third generation field, which is the B, third generation field, which is the tau, and also this is a neutrino tau. So these are essentially mainly third generation. Then of course there is the charm, but the charm we can obtain it via a rotation from the top. So it's almost all third generation. And if this effect is there, so we should see a deviation in when we have the third generation versus the case where we have all the other generation, which because in the standard model we have, of course, a universality. So this is well quantified by these ratios. These are X. X is any hadron here with a D or a D star. And this is the present combination of experimental result. Actually, it's not the latest update. There is a more recent update, but the situation has essentially not changed. There is a 3 sigma deviation here between prediction and observation. Of course, 3 sigma is 3 sigma, so we cannot be should not be overexcited, but it's interesting. Actually, this is persisting since quite some time. And so if we assume that there is this leptoquark, this would be the perfect mediator for this type of effect, okay? Because actually this is at 3 levels, so can compete with W, even if, of course, it's a higher scale, but with a strong coupling to third generation, make it compatible, I mean, to explain a 10% order of 5–10% deviation from the standard model in this process with tau. Another interesting effect, of course, another case where we have a mainly third generation field is B2S neutrino, because we can have neutrinos of the third generation. Of course, in the standard model, all the neutrinos are universal, but if there is new physics effect in third generation, that is one of the few observable where the effect is enhanced, because again, here we have a third generation field, third generation, so the only one is, we only get one suppression factor from the light S field. And what is nice is that if we take this model here, okay, here we can close the loop, we can predict the effect here. And actually, there is an unambiguous prediction of an enhancement of B2K nu in the model with the vector quark, given if you try to split the previous anomalies in RD. And this prediction was made well before observation. Now there is an observation done by Bell 2, which can still, the error is big, is another 2.5, 3 sigma tension that goes exactly in the right direction. So this is very interesting. And remaining in this process, actually, one can also look at S2D neutrino, because again, here we look at neutrinos of the third generation, and with mixing, we can also go to the light families. So, and basically we can describe all the operator, okay, affecting these 4-point function in full generality. And basically there are essentially only two types of operator, depending on here if you have a leptoquark or a Z prime. And these are these two operators. If you put all the bounds, all the observable, right now we have the following picture. So these are the bound coming from the B2 K nu and K2 pi nu. This is the collider bound, because in this case, this you can bound it also from collider, from BB to tau, for instance. And then there are electroweak precision tests. And actually, when you put all things together, there is the sigma is only, the tension is only 2 sigma. So certainly there is no reason to think that the standard model is off, but it's interesting that the central value is far from the standard model prediction. And here we analyze what could happen in the near future, just by in the next 10 years with the improvement at a high luminosity LSC that will reduce the error here, and by the improvement on the flavor observable. And this is what could happen if the central value remain what it is. So actually one could completely resolve this at the 5 sigma level. So it's quite interesting. And you see here the interesting complementarity between K pi and B2K. Finally, but last but not least, of course, this new physics, if it is coupled mainly to the generation, could be seen at the collider, because we can produce also big quark collision at the collider. For instance, if there is this leptoquark, you can expect a process of this type where you have BB going to tau with the T-channel exchange of the leptoquark, or if there is a Z prime, you expect again in the S channel. And here, now, the CMS and Atlas started to search for these things. And interesting, I mean, in all the channels that they analyzed, there is some slight excess. I mean, again, not a single case where we should be overexcited, but it's nice that actually you see here, for example, these bands are the region preferred by the low energy data, and present data seems to start to attack this interesting region, and with few sigma tension. So actually, this is somehow a summary in the model with the leptoquark, where basically the orange band is the region preferred by the low energy data, and this gray line is the bound recently derived by Atlas, which is not as stringent as it could be because there is a slight excess. And this is where one should hope to go at the end of high lumi, so basically covering most of the parameter region. And so this brings me to the conclusion. I hope I convinced you that flavor physics is still one of the most interesting aspects of the standard model, and at the same time a great opportunity to try to understand what's beyond. And this idea of a multi-scale construction at the origin of the flavor hierarchy, so the origin of particle masses, has several interesting aspects. And the key observation is that this idea of a new physics coupled mainly to third family could offer a nice way to both accommodate a relatively low new physics that can address also the electroweak hierarchy problem, and explain also why the light families have small masses. And so I think there is a lot of interesting still work to be done here, both on the theoretical and the experimental side. So I mean, the key message if these ideas are correct, no sound effect could emerge soon. I mean, even in the next year with more precision fixes. Okay, so thank you very much. Sorry if I said too many things. I hope at least something was understandable. Let me stop sharing.
Thank you very much for the very nice talk. Question from the audience? In your analysis, in your particular model, did you study some bound from charged lepton flavor relating processes, or for example, this electron conversion via the chain quarks?
Yeah, sorry. Yeah, there are bounds. Maybe so there are bounds from various type of searches. We look at, for instance, tau to 3 mu is an interesting bound, but are not as stringent as those. So you see, at the end, the most stringent bounds come from, in terms of low energy observable, the most stringent bound come from universality test in tau decays. We're really looking at tau to mu versus tau to e, and deviation from the coupling of the tau with respect to coupling of the muons simply in charged current interaction. These universality tests, which are quite precise, still from lab time, are the most constrained aspect.
There can be also some prospects from this.
Sorry?
This quark decays, because in your model, the first and second one, so maybe there are some sensible.
So sorry, can you repeat, because I think
there can be also maybe some.
I cannot hear you anymore. Can you hear me? Sorry, Antonio, I think there was an interruption.
Sorry, my internet connection is not very good. Okay. I was asking if there is some prospect also, maybe regarding this relator quark decay.
The top quark also I think is not super promising because the top quark decays too fast. So since the width of the top is very big, then this effect, we look at it and it's not competitive to the bound from B physics. But top, on the other hand, is very interesting for collider, in the sense that one expects in all this model, one expects some excess in TT bar production, for instance, because top, I mean, should be strongly coupled to this new physics. So and TT bar production is a good observable for so another very strong bounce on the model. For instance, also in this model with the leptoquark, you have not only the leptoquark, but you also have some heavy gluon like coloron, some couple mainly to third generation. So and these should imply some excess in TT bar, but for the moment we don't see. I mean, also there are some tensions here and there, but the interesting thing with top is to look for a collision with the top in the final state.
I see. Process like, for example, flavor changing to quark decay like THC. All these
this is small. It's small because anyway, once you put the mixing factor, you see that these are the bounds that you get from B physics when you rotate. They tell you that the rate are 10 to minus 6 or smaller, which is difficult to observe in top decays.
I see.
And simply because
Thank you,
simply because the
Gino.
top has a large width, okay? So then as a branch ratio turns out to be very small.
I see. More question from the audience?
I have a question. Well, first of all, thank you for your presentation. Very interesting topic. My first question is, according to in the first part of your presentation, you mentioned this. There are many dimensional 6 operators, like in principle, like 2,499, but they were reduced by some accidental symmetry, if I understood correctly.
Exactly. You got the point. So I was very brief there. So the point that here what we use is this accident. We really impose this U2 symmetry, that is the operator involving the light families have to be symmetric in any exchange somehow of the light family. So I mean the operator with up and sharp are identical, and this reduces a lot the number of free parameters. And we, of course, there is some slight difference, but we assume that the only breaking is the one which is already there in the U kappa couplet. So essentially only the CKM rotation, okay, nothing else. I mean, we work in the limit where basically neglect the mass of the charm, the up. There is only this rotation effect. And so we somehow impose this accidental symmetry, which in this setup is a remnant of the fact that the scale, well, the corresponding coupling agitator are very heavy. We expect not to see, we expect to have this accidental symmetry in this MEFT.
So how many operators after these accidental symmetries?
120. 120.
Okay, 120.
So instead of 2,500, we go down to 120.
Okay. And my other question is, in some slide you mentioned, or you put a plot. It was difficult to read because there were many models with this exclusion versus the energy of exclusion. I mean
the experimental bound.
Yeah, it was an experimental bound.
So yeah, this indeed was not meant to be read because indeed there are too many. So this one maybe.
Yes. So you're in the left part, in the left column, let's say, you are classifying each model by what?
No. So these are really, this is a table coming from I mean CMS reporting their.
No,
so these are all searches. Okay, searches. We differentiate. You cannot look, but sometimes a search for a leptoquark or a Z prime. So are all different type of searches. Okay, with the quark in the final state, lepton in the final state. So it's a classification of searches. If you go on the web page of CMS, you find this plot with all details. And then and they give different colors, sorry, depending on the type of search they do. Okay. On the other hand, here, what I circled are those which involve only third generation particles. Okay. And actually, what you don't see is the scale that this is 1 TeV and this is 10 TeV. For example, here there are bounds. Sorry, here these are bounds like basically they call it extra dimensional bound, but they're essentially are resonances, universal resonance coupled to quark. Okay, so here the bounds are very strong. So because you have a resonance coupled to up quarks, the bound is 10 TeV.
And in your opinion, what could be your favorite, let's say, ideas on to have this kind of things like the new physics coupling mostly to the third family of fermions? Just your feeling, what could be the best competitive models?
Well, I think some models of this type where this model here, for instance, I think we call it 4-3-2-1 model, or even model where we look at two interesting classes. Okay, one is this one where you basically deconstruct color, and we have this SU4. And another one is where you have SU2 right, which is non-universal. So you have an SU2 right for the light families and an SU2 right for the third generation. So a combination of these two seems to be the one more effective in at least passing well-present bound with a relatively low scale on new physics around 1 to 2 TeV. Well, more 2 TeV than 1 TeV, but still around 2 TeV.
And in that case, the leptoquarks, for instance, should be reachable.
Yeah, you see this you see it here. This is the leptoquark. Above 2 TeV, it's allowed. Okay, it depends on the coupling. That the coupling is sizable. For instance, this coupling can be 2 or can be 3, and then the leptoquark mass can, because basically, you see this line is the line of a constant effective scale, because effective scale is coupling divided by, sorry, is mass divided by coupling, because what enters is the, if you want to, when you mediate a process, you have a G divided by M, and this inverse, the lambda is M divided by G. And therefore, this implies a constant signal, okay? And this yellow area is the one that, for instance, can fit the present anomaly in B physics, and these are the present bound from direct searches, and these bounds should improve significantly in the future. So this is a projection. This dotted line is a projection at the end of high Lumi. So this, I think, is interesting, and we have something similar for W right field, okay, and Z prime.
Okay.
So something between 2 GeV and 2 and 3 GeV is absolutely accessible. You cannot go much more for TeV, because then the coupling becomes too big, so you enter a non-perturbative regime.
Okay. Thank you very much.
Welcome.
I have a related question. So anyway, first, thank you so much, Gino, for such a great presentation.
Thanks for listening. So, sorry if I put too many things. I usually add.
So I was wondering, this thing of the bounds on the third family, which they seem to be weaker than the rest.
Yeah.
Well, the question is, couldn't be simply because just experiments are more difficult or less accurate, and there is not really a.
This is a fact. This is clearly the case. So clearly, experimenting in a sense is more difficult for the third family. This is why the bounds are effectively weaker. However, so this is a fact. So in a sense, new physics is allowed because experiments are weaker. However, what is interesting is that why we want to have new physics. In first place, I mean, for me, still the hierarchy problem is the main motivation. So I want to stabilize the Higgs sector. And the Higgs sector couples strongly to the third generation, not to the light generation. So it's interesting that experiments still allow a relatively no new physics coupled to the third family. And so you're absolutely right that this is because they are difficult. So this is why we have to work harder. I mean, including me, our experimental colleagues, but we should not give up. So the fact that in a sense, my message, we should not be depressed by the fact that we don't see anything, a nice resonance into electron, okay? This really is not so much interesting to stabilize the Higgs, while a resonance in BB and top is what we really need to stabilize the Higgs, okay? And in the old days, till 10 years ago, we were all working with supersymmetry. Actually, this resonance should be coupled to everything, okay? So we were searching them mainly in the easier channel, but now I think we have not found it, so we have to really change a little bit paradigm and search for non-universal type of new physics in the flavor sense.
Yeah, I understand. Yeah. Good, thank you.
More questions from the audience? If there are no more questions, we thank Gino
Was my pleasure. Okay.
for the excellent talk, for the nice and very complete talk. And we talk
Thanks to you. Bye-bye.
Thank you. Bye. Thanks a lot.